new screen here. Don't save. Okay. You lift a 7.3 kilogram bowling ball from a ball rack that is 0.610 meters above the ground and hold the ball over your head, which is 1.83 meters. What is the ball's gravitational potential energy when you lift it over your head? So we're looking where we've got this ball rack. Here's a ball rack. Here's you. And you want to lift this ball over your head to like this height right here. It is at this height. You want to make it go upwards to that height. Okay, so what is a ball's potential gravitational energy as you lift it above your head? So you want to know what PE is. What we're given the mass of the ball. Given the mass of the ball, it's 7.3 kilograms. We're always in kilograms. We're given the, what are we given? We're given the height of the ball rack. The ball rack height is, let's just go from here to there. That height is 0.61 meters. And from the floor to the top of your head, that is 1.83 meters. Okay, that's the height. So it depends on what we want for the height here. So what is the ball's gravitational potential energy above your head? So above your head, it's going to be using this height over here. And we know what G is. G is always negative 9.81 meters per second squared. Great. A little disclaimer about the negative here. We're talking about the potential to do work, so the potential to do work is going to be a positive number, even though this is a negative right here. The acceleration is downwards against this motion of the ball being picked up. But when it's at this point, that doesn't really, the negative really makes no sense. It makes no physical sense. So we can just cross that negative off and just use the value of it. That's what we really care about in this situation. And we know the height above your head is 1.83. We did not use this height because we're going over a head in this problem. So potential energy is mgh. So we just plug these values in. And of course, this is going to be in joules. So our final answer is 131 joules. Great. Next question. How much work did you do to lift the ball over your head? So we're thinking about from here to here. I'll use a different color. From here to here. How much work did you do? Right. So how much work did you do? Not how much work did gravity do. How much work did you do? The ball went with your motion, so it's going to be a positive number. We know that. So the work that we did, that was for A, this is for B. The work that we did was a force times a displacement. Well, the force that we had to apply was a mass times the acceleration. So we had to go at least against gravity. So mg, and then we had to go some distance here. We'll just call that s. So mgs. We know what m is. We know what g is. We can rock this party out. M, just substitute that in. S is going to be the difference between these two. So it's going to be 1.83 minus 0.610 meters. So you're going to get, as a total amount of joules, 87.4 joules. That is how many joules you need to lift it above your head. Great. C, suppose you drop the bowling ball from the height above your head to the ball rack. What would its velocity be just before it hits the ball rack? This is a little trickier. So you're dropping it from here to here. We're dropping for S, right? So let's use a different color. Again, a different color. We'll use teal. This is for C. So you're dropping it from here to here. So we know that the initial potential energy plus the initial potential energy will equal the final kinetic energy plus the final potential energy. Right. There's a couple ways of doing this. We could say that the potential energy, we don't have to use this actually. In fact, I'm going to just not use this because it's going to be a little bit confusing about what we're talking about for final here. I'm just going to use this, what we know about the work going upwards right here. So let's just do that. So we know that the work to move this up here is 87.4 joules. So we also know that the work going back down is 87.4 joules. Going up and down, it'll get you to 0 work. So the joules, it'll be 87.4. That's our work. So we know that. They work for over this displacement. That's our work. And our work is going to equal the change in our kinetic energy. Change in kinetic energy. Okay. I'm making this a little bit messy here. So let me just rewrite this. I'll rewrite work equals 1/2 mvf squared minus 1/2 mu squared. This is the initial velocity here. The initial velocity is 0, so we lose this entire term. This entire term drops off. Whoop, whoop. Back to TL. So if we rearrange this equation over here, we can solve for VF. That's what we want. So I'm going to multiply both sides by 2. 2W equals mfvf squared, like this, mvf squared. Now I'm going to divide both sides by m. So it's going to be 2w over m equals vf squared. Now I'm going to square root both sides. 2w over m equals vf. Right. So if you do that, you're going to get, I hope, I really hope, you're going to get 4.89 meters per second. Okay. I hope you get that as an answer. Good luck. Talk to you later. Bye for now.